All right, I think we can get started. Thanks everyone for joining today for the seminar on cloud-native geospatial tools. And I'm Dr. Zarr with NCICS in Asheville. And today we're gonna have a guest speaker, Dr. Rich Signell, who used to be at USGS Woods Hole as a research oceanographer and have retired 3 years ago, 2 or 3 years ago.
Yeah, I don't really like that word, but yeah.
But Rich has been a big champion of open source development in geospatial domain, especially with the Pangeo community. And I met Rich, I think, 7 or 8 years ago, 7 years ago, I think, when we were trying to do a workshop about open data at AGU. And so to use those like cloud-based tools and Pangeo ecosystem to accessing those like open geospatial tools. And Rich has been a great champion for developing those community resources, including those cloud computing environments for people to play with as a sandbox within ESIP, and has been maintaining that for ESIP for quite a while through AWS and other cloud service providers. And you used to also host the Pangeo showcase, right?
Yes, yeah, pass that along to Max Jones, thank God.
Yeah. But
He's doing a great job.
anyway, Rich has been a great champion of geospatial cloud native geospatial workflows. And so we're glad to have Rich here this week with us in Asheville. And we're doing a short course on cloud native geospatial workflows with NCICS. And we're going to kicking the short course off with this webinar at this seminar. So thanks for everyone to join this seminar today. And we are recording the seminar, so it can be shared with others who cannot join. And Rich, the floor is yours.
All right, thank you, Douglas. I'm glad to be back. I don't know, were any of you here 2 years ago when I was here and gave a talk? Okay, a couple of you. You'll see a couple of slides that are the same because I want to make sure everybody's on the same level field, but I call this talk the state of cloud native geospatial, which is kind of pretentious. I like this part though, March 2026, because things are changing so fast. And so this is obviously my understanding, or in my world, the view of what's happening in cloud native geospatial. And of course, this isn't my work, as Douglas sort of pointed out. I'm really kind of like a enthusiastic cheerleader for all the good stuff that's going on in the community. I kind of view my job as trying to find out what's the stuff that we can really use, because I do have a background in physical oceanography and modeling. And I came to this whole subject from a very selfish interest in sharing the model results that I was producing and being able to look at other people's model results. And with that, I have to go back. You guys probably remember this from a couple of years ago. But I love showing this little movie to begin with. Of course, it's a little herky-jerky on the Zoom, but this was really the inspiration for 7 years ago for this effort to try to do this simulation is 1 kilometer simulation for a year was in the ocean was, I think it was 50 levels, it was a petabyte. And so it was pretty clear nobody's going to be downloading a petabyte. And so this data set was essentially it's sort of trapped on the Lawrence Livermore computer where it was generated. And the only people who can really work with it are the people there, which is crazy, because if somebody has some instruments here, and they can throw them in the ocean and say, how well is this model working? Or, what could I use this model for? The people, Lawrence Livermore, are not going to be doing that, right? They're going to do a few things maybe and say, okay, it looks good, and here's the model. But you really need these models in the hands of as many people as possible. And how do you do that? So this Pangeo community was started. I'm not going to go through the whole background and community thing like I did last time. I just want to revisit, though, this sort of this original sort of platform. So this was, I think this was in place pretty much 7 years ago now. But this was a brand new sort of idea that at the time that you would work. I guess I don't have a pointer, right? Anyway, whatever, right? I'll just say it. So in the center there, we have in that blue box, we have something running on the cloud. And it uses Xarray, which is sort of like the heart of this system that represents a common data model for multidimensional data, like more than 2 dimensions, data cubes, 3 dimensions, maybe ensemble members, 4 dimensions. Xarray is really good at that, representing that model. It's really the NetCDF data model. So, and then below that was a parallel computing infrastructure called Dask, which would allow you to automatically parallelize your operations with big data. And if you had your data in a cloud-friendly format out on the cloud in object storage, the idea is that then all these different Dask workers can independently be loading data chunks of this huge data set that you're trying to access. And of course, you're not trying to work with a petabyte at any given time. You're trying to extract a few months of sea surface temperature or something in some region of the ocean. And Xarray allows you to do that, all that kind of selection, and then pass off to these Dask workers to do the work. And down at the bottom here, I had all these different ways that you can spin up Dask clusters. You can use your local CPUs if you're just on a laptop. If you're on an HPC system, you can use this Slurm cluster to actually submit jobs for your workers to do. And then on the cloud, there's things like Kubernetes cluster and Fargate cluster that you can use on Amazon, for instance, to have multiple processes loading data and doing part of the analysis. Like when you take the mean, each one of those workers can be taking the mean of that chunk and then combining it together to give you the mean that you asked for. And all that happens invisibly to you when you're working with Xarray. So all you have to do is set up one of these Dask clusters, and it's a little bit different on these different systems. And once you've got your cluster, then you just work in Xarray and everything, is nice. And then the visualization package that really was like the missing link was HoloViz, because HoloViz would renders data on the back end and then delivers pixels to your browser so that you can look at a model result like the whole globe, and then you can zoom in and it'll re-render that image. And then so you're looking at the US and you keep going in and pretty soon you're looking at like docks in New Orleans or something. And so the full resolution of your model is then available to you to just use in your browser. And okay, yes, and speaking of using in your browser, this is all running on some environment that's on the cloud, and you're interacting with your browser. So you're just typing in some stuff in your browser on a lightweight internet connection here. She's in the park with a Wi-Fi hotspot. And she types, the commands get executed remotely, and then like the plot comes back to her browser. So it's a very lightweight connection needed for all the heavy computations happening on the cloud. So this is, this was the state of the art. So last time I did a big long demo, so you can see how this works. I'm not going to do that this time. But the idea here, we're like doing an HV plot. You can't really see the syntax, but you can tell it's just one line to give you something that is a map of, that includes a base map behind it. You've got some widgets over here where you can zoom in, and it'll re-render the image and change the dynamic scaling so that when you zoom into Michigan, it's not just all purple, and so on. So, and then while that's going on, you can watch this Dask plus this Dask dashboard. These are each of these gray lines is one of the workers and all those little gray blobs are a job that it's done reading some data. So you see how all these workers are reading data. There's no white in between. So all these workers are very busy, like doing all this work. So this is kind of what I showed last time. This was the GWiz demo, 6 years ago. And this, we still use that today, I should say. It's not like that's gone away. And this is, part of the Jupyter, Xarray, Dask, HoloViz is what I just showed, but it's part of anything you do in this space is part of this whole Pangeo or Python ecosystem. So you can use, things like TensorFlow or PyTorch for machine learning or anything else, pandas. If you're working with big data frames stuff, and you want to use pandas, you can do that and integrate it all within the same system. So this, I want to just remind people that we want to do this work on the cloud, but we want to do it in this. I mean, you don't have to do it in the cloud. You want your data on the cloud so that everybody can access it, but your compute you want to be able to bring it from any cloud like Google Cloud or Amazon, but also maybe from your HPC resources like an NCICS or a DOE or this institution here. If you're on a fast part of the internet, you should be able to bring your compute from your local, from your local hardware as well, right? Or maybe host the data on the local hardware in object storage. So, so this is just a little plot. I think I showed this last time. I updated this a little bit. You want the data to be stored on the cloud, but you want it to be free to access from other clouds or from HPC centers. This is open science. If you just park your data on Amazon and tell people, hey, the data is there on Amazon, you have to pay to get it, or you have to use Amazon Compute, that's not really an open science. That's not what we want. So this is just the cost of storing a petabyte per year at without some kind of wild negotiated price, which sometimes they do. But this is just the listed price for what I would pay for Amazon S3 for a petabyte for a year is almost 300K. And Google and Azure, okay, Azure's a little cheaper at 200K. They're both I think what's interesting is they're both the most expensive, and they charge egress fees. So unless you're, I know that you guys are part of you got a deal with Amazon and Google, or some people have deals where they'll host data, or if you could submit your data set to the open data programs and they'll host it for free and there's no egress charges. But if it doesn't get accepted, what do you do? Like if you have some data that they're not interested in, but you're interested in it, and you want other people to access it, then you have you want to be using these options over here. Cloudflare is probably the biggest company that's around that charges less for storage and no egress fees. Wasabi charges quite a bit less, but it's kind of a weird smaller company, and there's some issues like when you update things, like you have to pay for a certain amount of time. Every time you change the data set, you end up paying more. So like this might go up. This Open Storage Network and things like it. Open Storage Network is an NSF funded project that you buy you essentially pay them for a rack that goes into an HPC facility, and that rack is optimized for object storage, and it has a petabyte of storage. And so over 5 years, that's guaranteed lifetime of that thing. The cost per petabyte ends up being 24K, plus there's a little bit of charge that you pay the Open Storage Network folks because they actually maintain the software and keep it up to date. And I just wanted to mention this. I think I mentioned it last time, but I want to mention it again just because when I was at USGS, we found this to be a super effective way of distributing really big data sets that the open data programs weren't interested in. Now, NOAA, I guess, you have better deals with some of these cloud providers, but basically what we did was we had a cooperative agreement between the USGS and an academic institution, like I think, was fairly common. We actually gave our cooperative partner, the academic institution, a couple $100K. They bought 2 petabytes of storage, which they put on their HPC system in Woods Hole, in Western Mass in the Holyoke Green Computing Facility there. So we had 2 petabytes of storage on super high speed Internet 2 network, and that was where we parked a lot of our big data sets and no egress fees and super cheap storage. And a lot of some of the European groups I'm working with are basically taking the same approach of buying hardware for open storage, open object storage, hardware for object storage, and parking it on their HPC systems, and then making it available through S3 protocol, the same as with any of the other buckets. So I'm not sure I mentioned this last time, but I just want to make sure I do mention it this time, is that somewhere along the way, I think Ryan Abernathy in one of the calls or this blog post said, all scientific data is chunked. You're like, well, wait a minute. I thought only NetCDF4 and some others. No, because a NetCDF3 file, you write a certain amount of data, so the model takes a time step and you write some variables out, and each one of those variables that you write out is a chunk of data somewhere in this file. And so with NetCDF4, HDF5, you get to specify sort of how you want that data sub-chunked, and then you can specify kind of compression schemes and things. GeoTIFF, same kind of deal. Grib1 is actually the whole spatial domain in one time step, essentially, or one layer. or in grid2, but then they're compressed, but so they're chunked. All these different scientific data formats are chunked. NetCDF3 contains chunks that are uncompressed. All the rest contain usually chunks that are compressed. GeoTIFF, I guess, can also be uncompressed. And so, you know, that's one. The chunking is one thing. And why do we care so much about chunking? We actually care about chunking on file systems, but people didn't really worry about it too much because on file systems, it's really fast to get these chunks. So this is a regular file systems on the left and cloud object storage on the right. You have really speedy access to the chunks of data on a file system. And object storage is takes quite a bit longer, but everybody can be accessing those chunks at the same time. So I think it was Tom Nicholas in a blog post. He had this analogy I kind of like. It's like if you want to make yourself a sandwich, and you went to the fridge and opened it up, and you're standing in front of the refrigerator and you're grabbing your cheese and your mayo and your ham or whatever. It's pretty quick to grab all that stuff. But while you're standing there in front of the fridge, like nobody else can make a sandwich because you're like blocking the refrigerator. So like file systems get blocked. If you open a file, it's not like everybody can keep access that same file at the same time. On the cloud, with object storage, they can. So it's sort of more like everybody was getting their sandwiches from Amazon. You can order your cheese and your meat and stuff, and okay, there might be a little. There's going to be a bigger lag there. Luckily, the object storage is not like 2-day lag, but it's sort of the same idea. Everybody can order that stuff all at the same time from Amazon, and it works. So that's sort of, I don't know how well that analogy is. Is that a good one or no? Like thumbs up, thumbs down? Yeah, kind of weird. Anyway, okay. So if you look at a netcdf file, netcdf4 file, for a long time we thought that netcdf and HDF were just not performant on the cloud, and so the Zarr format was invented. So, and if you look at one of these files, like a typical netcdf4 file, there's going to be some data, there's going to be a little bit of metadata, some other size data, because each data chunk, even though it may be the same array, gets compressed a different amount, and so it has some different size. And then a little bit of metadata, some more blah, blah, blah. And the problem was that when you read this with a netcdf library or HDF library, it would go and read this little bit of metadata and then come back and then read a little bit of more metadata, and eventually it would read a data chunk. And all those little metadata transactions were killer because the cloud is a little bit slow for the first byte. Okay, so they said, okay, let's come up with this Zarr format where you can just take each one of those little chunks and put it in a separate object. And we're going to have the metadata going to be separate from all those data chunks. So each chunk becomes an object, and the metadata becomes separate objects. And it worked really well. And that was what was being used in those demos in the beginning, this new Zarr format. And then it's some of the good things about it. Like it was driven actually from the community, not from like the HDF group or the netcdf group. And so, I think it's better when things come from bottom up, instead of being, sometimes there would be a new release of HDF or something that would start breaking things and so on because the community wasn't ready and hadn't been involved. Okay, actually, this is just an example of when you look at one of these Zarr format, you actually look at what's going on in there. This is some data from AdCirc, and if you look at one of the variables, so there's like the data set, and then each variable is sort of like a folder, and below that there's these attributes that are all very readable. Those are the standard sort of things you'd see in a netcdf file over there, coordinates and units and stuff. And then there's this other one, Z array, which would tell you, okay, these bytes, what's the chunking in this byte string that we were reading, and what's the compression and stuff like that? What's the format? And then when the chunks themselves had simple names like the chunk zero, the 0/0th chunk of the data set would be 0/0. So you just read the chunk, the file or object called 0/0. And so if you wanted, you could very easily just read exactly the number of chunks that you wanted to. And so this all worked great, except that people were kind of freaking out and said, like, what, we have to convert all of our HDF5 files to NetCDF, or we have to convert our entire GRIB archive to NetCDF or to Zarr. We have to convert everything to Zarr to get cloud performance. Like, we have 40 petabytes of data. Like, are we really going to do this? So, this Icechunk was, the idea came about where you can use the Zarr library, and then, of course, the NetCDF data model and Xarray. But instead of actually going and reading the chunk from a separate object, you read from a range request into a particular object. Well, turns out that works great because you can read lots of simultaneous requests to the same object. And all you need to do is do one slow process first where you pull all the metadata out, like traditional metadata that we think about, plus the byte ranges of all those chunks. And all that goes into a file then that you read once. And then you have all the metadata, and you can just go start getting byte ranges from whatever kind of scientific file formats you have. And this was a real breakthrough because at this point you realize, actually, the file formats don't really matter. Like GeoTIFF, NetCDF4, HDF5, it's really about the chunks. It's really about the size of the chunks and the shape of the chunks. If you make it this will make it as efficient as possible to read all those chunks, whatever they may be. Okay, so this basically sort of standardized the reading in a cloud optimized way of all, our scientific data archives. I'm not saying that they are ideally chunked and you're stuck with those chunks unless you want to rechunk, but this is this great first step usually. So, Zarr, that was Icechunk. And so this is, I think 2 years ago, we weren't really using VirtualiZarr. VirtualiZarr came onto the scene when Tom Nicholas and some other folks realized that we can actually use the same Xarray sort of language and tools to work with what they call these manifests, where you create a virtual data set. You open up a NetCDF file as a virtual data set. And then you can actually here, you can look at one of these things like 0/0/0 again, is like a path to a NetCDF file with some offset and some length in bytes. And you work with these things, like you can concatenate these things. So you have a list of NetCDF files, you create these virtual data sets for each one with VirtualiZarr, and then you can say like Xarray concat and create one virtual data set. The other nice thing about VirtualiZarr is that you can just say to Icechunk, and Icechunk is a, we have a slide, the next slide is about Icechunk. Instead of just storing these references as a JSON file or as a Parquet file, as we did with Icechunk, Icechunk is something that Earthmover developed, which is where a lot of the brain power in the Pangeo project ended up. And it's like a repo for your virtual chunks in this case. So it keeps track of all the chunks, all the references to the chunks. And if something changes, you can append or change and commit and get a new identifier for that data set. So this is like the reproducible part of like FAIR, that you can actually go back and get the data set that that the workflow used, because it has a hash on it. So, and this was, this little picture on the right is basically if you don't have Icechunk, like somebody starts writing some new Zarr data set and they're like writing little chunks of data, or maybe the NetCDF files with references, and somebody else tries to access this thing, it's a fit. Like with Icechunk, you only get to access it when the whole thing is in place and it's verified that all those pieces are actually what they were when you created the file. So it's a little bit about stack. So we talked a lot about these, how we create these data sets with archival data and the reasons why we want to store them on the cloud and the approaches that we use to access them efficiently. We also want to be able to find them. And so if you want to find, like, you got a bunch of models and you want to find the ones that, had some temperature data over Cape Cod Bay for the 2 months that I'm interested in it, it'd be kind of nice to do a query and get back, okay, here are these 4 models, and then start just accessing the data, right? And so the stack Spatio-Temporal Asset Catalog concept came out of the remote sensing community. And again, it was developed from the bottom up. So they were building tools as they went along with sort of building out the standard. Started out just for remote sensing data, but there's lots of extensions for all sorts of things now, including CF conventions and model output and Icechunk and all sorts of stuff. So right now, you can use it to query model output really effectively, and there's some sort of newer work in France, I think, and elsewhere to actually see how well we can query things like LiDAR data and other in situ observations. So the hope is that you could actually just do some stat queries, find all the data that is relevant to your use case and all the model output, assess the quality of the models or use them, whatever you want to do. Oh, and, these stack items, they contain things like, the geometry of this thing that you have. If it's a curvilinear grid, maybe that's that polygon that covers your curvilinear grid. And then there's a bounding box that goes around the whole thing. And you have a temporal extent, and then you have these assets where you have the information that you need to then, like, open up the data set in X-ray. So, what this looks like is just for a particular, okay, you can't read that probably from the back. But maybe you can, I don't know, maybe you can see that there's an ID for this data set, there's a description, there's a start time and end time, and then you see things like cube colon dimensions, cube colon variables. That's a cube, that's the data cube extension. So when you see one of these things, colon, that's an extension on the data model. And then you can see here, there's a bunch of variables, in this particular stack item. And then if you scroll down a little bit further, under storage, like assets, under assets, you can then see like this Icechunk information, the snapshot, and blah, blah, blah. And that's the stuff that allows you to then open this thing up, open up your the query that you got back in Xarray. So this is just like an example of, like, once you've got one of these things, this is just a nice tool called the Stack Browser, where you can take your catalog that you've generated and just chuck it into the URL of this Stack Browser, and it will then render your different items in this sort of nice way. And if you click on one of them, then you get the different ways you can access it and so on. And I'll show you that in just a second. So this is one that I did. I did this for all the, basically all the NOAA weather data that dynamical.org has turned into Icechunks. So I just wanted to test this out with a bunch of publicly available Icechunk data. So this is a super convenient way to access any of this data. The GFS forecast, the HER analysis, the HER forecast for 40 hours, blah, 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 ECMWF. All right, so I've talked a lot about different web, different ways to access this with Python. Well, what if people are trying to access this information, want to access it from just a web browser without Python? Well, one way to do it is to deploy Python-based tools that have some user interface. Like you can take a HoloViz dashboard and you can publish it, as a container with a port open, and people can interact. Actually, this is actually on the bottom left is like a little search and rescue application that my partners in Italy did, where it's the user clicks on a map and then they specify what kind of, if it's a person floating in the water or whatever, and then they can say, I want the ECMWF winds, and I want these local coastal ocean model currents that are coming from this ice chunk, and so on. And that's one way to interact. Another way is that Earth Mover after some work with IUS. I see Micah's on the line. IUS and their cloud project worked a bit on these Xpublish based service layers, and then one of those guys, Matt Iannucci, who did a lot of work on that, is now at Earthmover himself. So Earthmover released this Xpublish tiles package, which you can then deploy. So you have to deploy it. But what it does is it provides a web map service API, tile service API, environmental data retrieval API is available as well, or even OpenDAP. And when people access those services using those standard APIs, then on the back end, it actually is doing all this stuff of opening the data in Xarray and using maybe using Icechunk and all these other things. So that's another way. So this would allow someone, say with Arc, so say with a GIS system, which can accept OGC tiles to access model output, into a GIS like QGIS or Esri products. But the coolest way is something that really is just been available for the last few weeks, maybe. There's various forms of this, but is JavaScript directly accessing data in Icechunk and in Zarr. And this is, I don't actually know who did all the work on this, but there was a great talk by Shane Loeffler, I think his name is, from Carbon Plan on the Pangeo Showcase. I think it was just last week, maybe the week before, where he demonstrated this package called Zarr Layer. So Zarr Layer is a JavaScript library, and so I do actually, I think I hopefully have. So this is just a little. I figured you have to do some kind of live demo. So this is just this is not although it looks like a tile service, it's not a tile service. It's just the browser making direct requests through Icechunk to these to this Zarr data set. In this case, it's this another one of these dynamical products, the GFS forecast. And if we switch to like the HER or something, so here's the HER forecast maybe. So then, have I even tried this? I'm not even sure I've tried this.
It's dangerous.
Yeah,
like them.
Yeah, really. Or maybe I was also having some weirdness with this is going to be slower actually because it's not chunked. It's chunked quite differently actually. Well, actually, let's just wait. Let's wait here and see if this updates. So one interesting thing about this though is this is just really reading the analysis, the full resolution model output, and so it's just reading that Icechunk repo that dynamical.org created. What the really interesting thing about the talk was, actually, I'm just gonna, we'll come back later to see if that, or maybe I should switch back. Let's just see. Let me switch back. Oops, that's the 1.0. Let's see, let's try this one again. I was having some weirdness with the browser and Zoom before too, so maybe. Yeah, although we just did see it update though, right?
GFS did fine.
Yeah, so let's try switching to something else and see if it. Oh yeah, okay. So anyway, here it's going off to access the total cloud cover data, and I think I should be able to click a spot and 100% cloud cover, 0%, whatever. That's not so interesting, I guess. But anyway, you get the idea. Like, so this you can wander around and pick the different data set and pick the different variables and whatever. And the rendering is happening in your browser. Reprojection is actually happening on the GPU in your browser if it needs to reproject, which is pretty cool. And I think the coolest thing about this.
So what they are saying is there's no backend infrastructure needed except the browser.
Yeah, so we'll be able to in our workshop later, hopefully we can create some of these pointing at like Icechunks that we create or whatever. And we won't need to deploy any infrastructure on Amazon and keep paying for it. Like I deployed a map server, like I deployed that, the Flux layers thing, but I'm paying for a thing to run that container all the time. And then if a bunch of people hit it, it's going to get overloaded. And services kind of suck. Services were great for a while, right? Because they standardized everything, but now we just want to go right to the data. And so, so this is pretty exciting. And at this point, I guess I want to mention that, like that app that I made that app. Well, actually, I didn't really make the app. Claude Code made the app. Like, I don't know how to program in JavaScript. And so coding agents have totally changed the game in terms of all the Python tooling you're seeing coming online, but also JavaScript application, everything, right? Like, and I think it's kind of interesting. Like, this is a Claude Code generated table comparing traditional coding with vibe coding, although you might like to call it agentic engineering. Yeah, but anyway, it's the traditional coding. You have to learn how to program some kind of language and use some IDE. And with this, with vibe coding, you just use Claude Code or Gemini CLI or ChatGPT Codex. They all work pretty well. And instead of going line by line and typing in code, you just say, this is what I want. I want to have an app that displays these Icechunks in Java in a web browser. And I want to use this Zarr layer library. And it comes back and it does something and it's not quite right. And you say, like, you know what, fix that and add a color legend. And it's like, okay. So, you just sit this feature by feature, and instead of you being like the sole author of this thing, like you're like the director, you're the creator. You can create more. So I'm a big fan. And instead of manual debugging, you just like, hey, something's wrong here. Take a look at this. Here's my error. What do you think we should do? And it's just like, okay, I think I see what's the problem. I'll do this. So it's pretty amazing. So I have a couple slides just showing like there's a lot of big organizations doing this and taking the same approach. It's not just some weird thing from a few weird people. So the German Climate Service, they have this Erie project. They have this awesome stat catalog with all their stuff, and they do something I really like here, which is they stuffed a little bit of code into the description just to make it easier for like Python users to just grab this and load it right into Xray. But they have all their assets down there, different ways you can work with this data. And one of them down there at the bottom is visualization with grid look. So they've got their own thing that goes directly to the data, doesn't use any services. It goes right to the S3 requests. So they've got their own little spinny globe thing and all sorts of cool stuff. And this is the thing that's coming that is super, super cool. This was the thing that Shane showed 2 weeks ago, where the app that I just showed that is accessing Zarr directly using Zarr layer. He showed how you can have these virtual references accessing the foundational data, right? The analysis, the full data, the full resolution data. But then you can actually use this Zarr's multi-scales convention to build, just like in a cloud optimized GeoTIFF, you can build an overview layer that's like 1/4 the resolution, and you can store that in a native Icechunk, and then the 1/16 or whatever, how many you want, you store those in native Icechunk, and they're small compared to the big one that's still in your NetCDF or GRIB or HDF. And when you have all that, you can just blast through these visualizations just like COG. So, Cloud Optimized GeoTIFF was the big thing. Like, oh my God, you can look at how great you can visualize this with remote sensing data. And everybody in the modeling community was like, oh man, I wish I had that. Well, now you have it. So this is what we might play with this in our little workshop too. This is super cool. Oh, I just wanted to show this. Well, you can't see this in the back either, but as you zoom, and if you have the developer tools open, you can see it's like hitting what layers it's hitting, and eventually when you get in far enough, it starts hitting the NetCDF files, which I think is kind of cool. So so this is this modern approach. So you have your legacy NetCDF files, you use VirtualiZarr to get the references, stick them in Icechunk, and those are your native chunks. And then these coarser resolution chunks are sorry, these are the native. No, sorry, the original foundational files are the full res, and then these are these native Zarr chunks using this OME Zarr multi-scales convention, and then visualize on map or with with Python the way you always did. Just a plug for Earth Mover, like this is again like where most of the really creative and talented people in our community are working now. They need money. It would be great to support them because they keep doing good stuff and putting out open source, great open source stuff. So I know that they're looking for more people to buy into their product. If you buy into their product, really what you're doing is just sort of using all this same tooling in a way that they're managing all this stuff for you. So you're still using your own like cloud compute and things like that and your own data stores, but you can use things like Array Lake to search across all your data and keep track of anything that changes in your data. And you have this Flux service, which is on top providing the map services, although maybe those aren't maybe going to be as useful anymore. And then there's this marketplace where it makes these large data sets, both public and private, sort of available to you to use. So second to last slide here. If you're a forecast modeler, so the folks I work with in the I work with this global coast project where the idea is that there should be anybody in any region in the world should be able to, if they have some problem in their coastal ocean, they should be able to spin up a coastal ocean model and start doing like forecasts. And and the boundary conditions are coming from another model and so on, and the data all goes onto the cloud, all the same stuff. In that case, this is the workflow. We run the model on the cloud. Either it's Dockerized or we're using one of the custom, sort of tooling that the cloud providers all have for HPC, like Amazon Parallel Cluster. As soon as we get the output, we either re-chunk it if we need to, like maybe we give it more time steps than one in the time dimension, because we always tend to write these pancakes out. The data runs for one time step, we write the model out, and then we write another one. And so, some in a forecast model, say that's 5 days long, and it's hourly output, say we might re-chunk that netcdf file into something that is not the whole spatial domain, but is maybe like 1 day, so 24 hours in one of the chunks. And that will make reading time series much, much faster. And then we still store that netcdf file as a netcdf file though. So all we've done is like used like NCO tools to like re-chunk that same file, so it's a little bit faster to access in time. It's still 1 5-day forecast, and it's a netcdf file. And then we just push that up to, and then we also add maybe CF conventions or add like UGrid conventions if it's unstructured grid, and SGrid conventions if it's a structured grid. Anything else that we might want to add to make it more accessible by community tooling, and then push that netcdf file to the cloud. Use VirtualiZarr to create the references, store the data in Icechunk repo, commit the new references. So we have the same Icechunk repo and we just commit the latest forecast file, and then we update the stack. And then our downstream apps, whether Python or JavaScript, access the stack catalog to find the resource that we're going to open up and start working with. So, the benefits of all this for FAIR, it's, really supports the FAIR principles and open science by leveling the playing field. Again, as I was saying, anybody in the world can do this with the cloud. We're really working toward this ability to be able to do whatever we want with the data, just picking the pieces that we needed, but without anything like OpenDAP and these threads data server services and other things like that. And because you want the tooling, your model output to work with this tooling, you still need to have standards in the metadata more than ever, really, because there's no service that's going to be in the middle of this that's going to be helping you out. Your data itself needs to have the standards in there. And then, of course, the cloud, everything, commuting becomes a commodity. You don't have to, invest $300,000 for a new suite or $1 million or whatever for a new supercomputing center. And just buy what you want when you need it, and it works great for small data as well as big data. And again, pay for only what you use. I don't think, except for like super big model runs, like I don't know too many people who have like gone back to like, unless they're like heavily subsidized for their local computer or something. I don't know too many people who've gone back to local, on-prem computing after taking some time to understand the cloud. So, okay, that's it. Thank you very much.
Thanks, Rich. Let's see if there's any questions. I think we might have some questions already on via chat, but so if you have questions, please raise your hand so we can go through if you're online, and we can start with some of the in-person questions as well. So while I'm trying to pull things up for the Q&A, there's some chats happening, which is too small for me to see at this moment.
Oh, yeah. Maybe I can see from the.
But any questions in the room? Can you say a little bit more about Icechunk for version controls? Because I think you mentioned that in the slides, but you haven't really talked about how people can do version control with Icechunks.
Yeah, yeah. So every time you change, so before, as I sort of alluded to, like if you updated some Zarr files or something like that, and nobody would really know. You just have like a URL that is this, is your Zarr data set. So it could really be anything, or it could be broken because or it could not be, somebody maybe updated some of the parts of it and it still works, but now it's different. Icechunk prevents you from doing that. So it keeps track of all the timestamps of all those chunks and when you actually made the commit on the repo. And so you have a unique, stamp for that particular data set. You could still break it. I mean, you could still break it by deleting like some of the files or something, but at least then it's broken. Like you won't let you, it'll say like, this is broken, but the best thing I think is that, every time we push a new forecast, we get a new stamp, and that stamp goes into the stat catalog. And and you can still go back to the old stamps if you actually, that's an interesting question. Like what do you do with the old stamps in the in terms of like maybe you want to go back to one, but now it's not in the stat catalog anymore. Maybe you have another stat catalog for everything. I don't know.
Yeah.
There's definitely some unanswered questions about stat.
We have a question from Micah. Micah, do you want to ask questions by yourself? Because it's a bit small for us to read from the chat.
I think Micah, are the dynamical Icechunk repos you showed in the stat catalog reinforcing the? Okay, maybe I need to read it on the screen. Can you read it on your screen or?
Let me move it to my screen. Okay, yeah, I can do that. Micah asked, are the dynamical Icechunk repos you showed in the stat catalog referencing the source weather models hosted on NOAA Node and Open Data Dissemination Program? Or is the data replicated to Zarr first for the dynamical?
I bet Micah knows the answer. But yeah, no, actually those data sets are rechunked and written in Zarr, native Zarr. I have been in conversations with Dynamical about that they are interested in also doing the references, the virtual Icechunks for some of the data sets as well, because they can't afford to replicate. Those data sets also don't contain all the variables that the original data set do. So that would be kind of an interesting way to go, right? To have a virtual data set that was everything. And maybe it's not quite as performant for certain use cases as the native rechunked one that you did, but couldn't afford to do it all over again. So, and I always view the virtual thing as being the first step. So do the virtual thing and see if it actually is okay. Now, is it good enough? If it's good enough, fantastic, because yeah. And sometimes it's as good as it's gonna get because you're not going to rewrite 80 petabytes or something. So, but sometimes, if there's enough need and if the data is not too big, then maybe you can't afford to keep another copy of it and keep updating the rechunk data and all that stuff. And so that's what Dynamical is doing right now. I'm not sure who's funding them to do that.
Okay. So there is a question from Shane Mill. So does Zarr layer access data through Stack API or directly from object storage?
Well, so in that app that I showed you, it actually it finds the data set, it finds all the dynamical data sets that are on it goes to the stat catalog and queries the stat catalog and finds the Icechunk assets, and then opens those Icechunk assets and accesses the data directly from the Zarr stores on S3. on Amazon Open Data.
Okay.
Amazon Open Data? Yeah, Amazon Open Data.
Yeah, dynamical
Yes,
work
yeah.
there on the
Yeah.
open data. There's a question from Charlie Burris, where could we see the stack metadata? So I guess it might be referring to the stack browser.
Is this for the dynamical?
Yeah.
For dynamical? I mean, that's something that I just sort of did as a, proof of concept, but I think dynamical themselves is going to be hosting their own. I passed that along to them. They're like, oh, that's cool. Like, we should do that. And so I think they will be doing that themselves, but I could certainly pass the URLs along. I'll keep them going. I mean, it doesn't cost me anything to do it. So, but then eventually there'll be a better stack. Actually, so that was something we were talking about with Otis just before this meeting. I mean, Stack doesn't exactly, help you find anything in the world, right? Like, even if everybody was using Stack, how we actually coordinate between different Stack APIs, you can imagine there's 200 Stack APIs that you need to query to find the data that you're interested in. I mean, that might be okay. And maybe we figure out a way to automatically update Stack if somebody deletes a data set somewhere. But those are things that are not working yet. But at least there's people talking about those issues and trying to build together from the same common framework.
Okay. Another question from Roland. Python access seems pretty well understood, but we have folks using our data from R who are having trouble bridging between the Python XArray environment to their R workflows. Do you have any suggestions when working with different programming languages?
I mean, they just need to build the tooling. I mean, I just saw there's a new Zarr, package out for R just like last week or something. There's definitely Zarr readers out there. But I don't know if they have all the features, so JavaScript just got the ability, right? Like Python's had it for whatever, 5 years or 7 years now. And we've just sort of gotten the ability with this Zarrita package that's underneath Zarr layer to access these Zarr. And, but it's a standard, so for sure it can just be used in R, just like in Python and JavaScript.
Okay, another question from Eli Holmes. Are people not creating native Zarr now? Is it better to create NetCDFs and the VirtualiZarr a sidecar with the products?
That's a good question. I mean, it really depends, I guess, if you feel like your community still wants NetCDFs for some reason. And I feel like a lot of people still do. But that's going to change too. And so when we get to the point where everyone can read Zarr with every tool just as easily as they can read NetCDF, then we don't need the NetCDFs anymore. And we'll be writing just native Zarr, I suppose. It'll take a while to get there though, right? Like I think NASA still has like HDF5 is like a mandated format for like collecting data. And so, I think writing native Zarr there's nothing, especially with Zarr 3. So Zarr format 3 introduced the idea of shards, which I didn't really talk about, but so I mentioned before, like in Zarr 2, each object was in a different object store in a different chunk. Each chunk was in a different object store. With shards in Zarr 3, you can put all the chunks back into the same object. So that starts to look a whole lot like HDF5 or NetCDF4, except that it's a community thing. And I think arguably a more understandable and better format for the future. So I think it'll go away, but for now we're still doing the NetCDFs partly because it makes people feel better. Like they like having their data still in NetCDF. And for the user, it's just as fast. Like and they don't care. So if they're accessing data from an Icechunk, they don't care whether it's a native store or a virtual store pointing at NetCDF. It takes the same amount of time to read the data.
I guess that's my interjecting my comments, which is that if there's a requirement for archiving, there's only certain data formats that's accepted as acceptable like archives.
Right. So we're gonna have to get to the point where it's acceptable to store data in Zarr 3.
Right.
Yeah.
All right. 2 more questions. Well, let me see if there's other questions other than from Eli. I want to give opportunity for other people to ask a
I know for a
question.
fact Eli's gonna go off and play with Zarr layer right after this. If she hasn't already.
There's a Steve Olsen from Weather Service saying he wants to tag up with you soon for because they're using similar tools for the weather service visualizations, and he's requesting for contact info. I can send that to Steve from Weather Service, and I'm gonna see. Okay, going back to Eli's question, how to deal with a swath data that is not on a regular grid and every granule has different dimensions. Do we have a virtualizer for each NetCDF granule for those type of variable like dimension in the data itself?
I mean, yeah, it does. I mean, with swath data, I mean, it's still, I don't think it really matters. I mean, going to some different format doesn't really, or some different access pattern really doesn't change the the nature of like dealing with swath data, I guess. I don't know. I mean, or maybe I didn't understand the question.
Eli, can you unmute yourself and then just ask follow-up questions to clarify it? Yeah, go
Yeah,
ahead.
Rich. So like when I've made a lot of like Zarr stores, and in that situation, um, each of my when I've done it, each of my layers needed to have the same like grid, the same dimensions. But when
I
we're
see what
working,
you're saying. Okay.
yeah, swath data is not like that, right?
Yeah. So you're asking if you can like sort of mosaic a bunch of swaths somehow into a data set when they all have different shapes and everything, right?
Different shapes, and then so you might have, let's say it's like a classic swath data where you have, let's say your dimensions are the number of pixels across the swath, and then the number of lines, so lines of your swath. Okay, so in the file it has those same names, but then one, the size of it's going to be different, but importantly, the your navigation data, like how it links what the lat long is for each of those, the line and the pixel, that's going to be different. So that's going to be totally different across each of your net CDFs. You've got these kind of grouped things where
Yeah.
you have your navigation data, your product data, your sensor data, yada yada.
Yeah, right. So I think you're still stuck with that. Like you could put it in a data tree, um, but it's still, or groups or whatever, but I don't think there's any way to, I don't think Zarr 3 does anything for you there, really.
Okay. Um,
Well,
Douglas,
yes,
could I ask the third question? Because I was most interested in that one.
go ahead. Next time you should put that question first.
Oh, okay. Sorry.
Go
Yeah.
ahead.
No, it's
Um,
great.
so I've wanted to create these VirtualiZarr files for like collections that I'm, working with, or I'm, teaching,
Mhm.
but I didn't know, like, if I host this thing, how do you keep it synced to the original data set? Like it seemed like, well, I can create it once, but if they change the original net CDFs,
Yeah, yeah.
what do I
That's,
do?
I mean, that's the thing. That's where, I mean, Icechunk will at least tell you that something has changed and it's not kosher anymore. So like, so you won't get people like making dangerous mistakes because they thought they were accessing some kind of data, but actually they're accessing something else, or that they got some weird failure because the byte ranges are no longer correct for that one file that got changed or something. It just won't let you do that. But I mean, but in terms of updating the references, yeah, if something does change and you want the data set to work, then yeah, you need to check that in and update your Icechunk repo.
Yeah, I think Eli responded, the Icechunk piece is the key to connecting, make sure that
Yeah,
it's the version control basically we
yeah.
discussed
I mean, I
earlier.
think the way Earthmover said is that it's like, it's basically Zarr for operations. Like, when you actually have to keep track of what the hell's going on, and you're not just goofing around, like playing around in academic space anymore.
Great, thanks. We're actually right on time for a 60-minute time slot. Thanks, Rich. again for the presentation. Thanks everyone for joining. And we will have the recording up on our YouTube once we finish processing it. And hope to see some of you in other venues that is relevant for Pangeo and cloud native geospatial tools. Thanks everyone.